All right, hello everyone. Today's lecture is on SQL database scaling, building off of the last topic on SQL databases in general, also called relational databases. So to start that discussion last time, just to review, we talked a little bit about how persistent storage, which is needed really for all applications, how that presents some special challenges, both because accessing storage is not something that's built into most programming languages, so it requires special actions like explicitly opening files and reading from them and writing from them and closing them and all that stuff. So a lot of low-level details there that you have to implement to deal with files. And also because storage devices are a lot slower than memory and other storage on a computer, both of those things make storage one of the main challenges in scalable systems, so we're going to be spending a significant amount of time on that. I mentioned how a database machine can use many disks together using a system called RAID that allows that one machine to have many disks working in parallel to increase the capacity and also to increase the throughput, so you can write and read simultaneously from all those disks. And we introduced databases and relational databases in particular, SQL databases, as a way to solve a variety of problems that arise in programs that use storage. So scalability in the sense that it allows you to access a large amount of data that's provided by files. Persistence because that data lives after the program stops running and is powered off. Those are things that are provided by file systems in general, so we could have just used files to get that stuff. What databases give that's a little bit unique is indexing, in the sense that you can have multiple indexes for the same data set that allow you to quickly find data elements according to many different criteria. That's really the big selling point, I think, of databases compared to more basic ways of storing data in files. And also, that's a big selling point of relational databases compared to NoSQL databases, that there's a lot more indexing available in a relational database because it's all in one machine. And the way relational or SQL databases are organized is by having a bunch of tables. So instead of having files that have an array of data, instead we have this abstraction of tables, and you define a schema to specify what columns are in those tables. And as the system evolves, when it gathers more data, that's represented by new rows being added to tables. Okay, so you define this schema ahead of time. In other words, you define the tables first, and that gives some structure to what the program is going to expect and be able to add to the database. Finally, having a separate database with a special query language called SQL allows us to do some analysis outside of our program, but essentially on the storage system itself. So for example, if we want to find the summation of a lot of numbers that are stored in a database, you can write a query for that. And instead of transferring all that data to your computer and then doing the sum there, that would involve a lot of data transfer because you're transferring all the numbers. Instead, you're just giving a specification for the calculation that you want. You're giving the query, and the database runs that query in an optimal way, calculates the result, and then just sends you the result. So you end up being able to move a lot of your analysis code close to the data storage, and that's really important for large-scale systems. That's also the concept that's used by systems like MapReduce and Spark, but at a larger scale. Okay, so today we're going to try to get into the performance issues in databases. We're going to start talking about those. So we motivated databases last time. We kind of showed the benefits of relational databases, but we still had relational databases as a central bottleneck in our system. We did show that we could use vertical scaling to make those databases pretty fast, but at some point they're going to run out of compute power or storage. Now, when you're working with a database, even if when you get to the point where your database might be a performance issue, again, you can think about getting a faster database, but you also can think about other ways to optimize that performance of that one machine. And one of those ways of optimizing is to make sure that it the database is making as few accesses to the disks as possible. Remember, the performance of memory, which is to say RAM, is much, much better than the performance of disks. So the latency to access RAM is about 100,000 times less than the latency to access disk. It's smaller, maybe about 100 times smaller, but these days you can get a server that has 1 terabyte of RAM, let's say. That's a lot of storage capacity. So it's very possible you could design your database with the intention that most of the data, although it is stored on disk, during operation you would expect that data to be mostly cached in memory, if you've provided enough memory for it to be cached, and if the active data set is small enough. So by active data set, we mean the subset of the data. I mean, all the data is stored on disk, but in general, there might only be a subset of that at a given moment within a certain time frame you expect to be using, because your application might have old data that's not frequently accessed. If that active data set, you want that active data set to fit in RAM to get good performance. Both the database and the operating system will kind of automatically migrate the most frequently and recently accessed data on disk into RAM so that it can be quickly accessed, again, taking advantage of that much lower access latency in RAM. So what does this tell you? Well, first of all, you could try to reduce your active data set to access less. If you access less data, that can actually improve the performance of your data, because it means that most of your data would fit in RAM. Secondly, it means that you can upgrade the RAM on your machine to get an increase in performance if you find that the performance problems you're having are due to slow I/O, a lot of data being transferred from disk. Yeah, both those things. Because generally you're going to be limited in the speed available on your processors and also on the disks. Disks are only going to get so fast, and they're always going to have significant latency, no matter how fast you make them, how much parallelization you build into the system. Okay. But regardless of how much we tweak these databases, eventually they are still going to be performance bottlenecks. So here is a typical system design with requests coming into a load balancer, going to many clones of an app, and then each of those apps contacting a shared database to save shared state or to return data to the users. It's a simplified, simple architecture. So I'm saying that the database is a performance bottleneck, but there also is another single point of there's another kind of bottleneck thing here, which is the load balancer. There's only one load balancer. There's only one database. You might think that either one of them could be a bottleneck. So why is the load balancer not a bottleneck in this case? And I'm saying the shared database is the bottleneck. I want you to stop and think about that. If you think back to the load balancer lectures, you should get some ideas for that. Okay, so hopefully you stopped and paused. Basically, the reason is, although it's true that every request is going through the load balancer, and if we also expect every request to go to the shared database, the problem is basically the load balancer is doing very little work. I mean, the problem is the shared database is doing a significant amount of work per request, because generally it's fetching data required for that request. In the case of Wikipedia, for example, it would be getting text to render back to the user. The load balancer, on the other hand, is just choosing among the clones to send the data to, which is actually a very simple thing, right? So load balancer is a single point of failure in this diagram, but it's not the bottleneck. If there was no database at all in this design, then in that case, you would say that the load balancer was the bottleneck. But in general, there's only one bottleneck that in a system. It's whatever the slowest, component is. And in this case, it's the database. So you might ask yourself, to solve this problem, to make the database less of a bottleneck, why not just clone the database? So just like we have apps, the app server being cloned, and we have many of those apps running, we could clone the database and have kind of a load balancer in front of that. And we're kind of going to be doing that today, sort of, in the next couple lectures, but not totally, because there are a lot of problems that arise when you try to clone a database. So I want you to stop and think at this point to see if you can figure out some challenges that would arise in trying to have a system with a cloned database instead of just one shared database. So stop and think. Okay, assuming you did that. The problem is, the biggest problem in my mind is that when you no longer have a single shared database, you lose the benefit of having the database serve for coordination. We said before, when talking about stateless services, we pushed out all the state to the database. If a request comes in that makes a modification on one of these app servers, that change is going to be stored in the database, and then if a request comes in to view that data on another app clone, it'll see that update that was just made. The way that coordination happens, in other words, that the propagation of state from one of these app clones to another is possible because they're all interacting through the same database that is kind of persisting those changes and making them visible to everyone else. Once we start to clone this, we introduce a big coordination problem because an update that's written to one clone of a database has to somehow be shared to the others in a way that makes it visible and also that's scalable. So basically in this lecture and the next one, we'll be talking about ways to sort of kind of clone the database to get some of that parallelization, but without having a lot of huge, while also solving the coordination problems that arise. As a kind of side note, before we get into those horizontal scaling issues, another thing I want to mention for relational databases is, so in addition to just getting a faster machine, there are features built into the database to make it efficient. And so one of those is a query planner. So when you write a query to run on a database, the database management system will kind of run an optimization program to figure out how to execute that query. It kind of compiles the SQL into a sequence of actual fetches from tables and scans and whatever else it needs to do to get the data that you need. And it'll try to, depending on which indexes you have and what the data is and what the statistics are of that data, it can make different choices, and some of those choices are going to be better than others. But I guess that's really the topic of the database class more than this one. Like I already said, RAM can be used to cache the most important data and also indexes, so you don't have to access disk as much. You also can have the database can actually have some caching built into it, so it doesn't have to check disk. If there are queries that are sent repeatedly, it can have cached responses for those, as long as it has some way to invalidate that cache when the associated data is changed. We also can try to just reduce the number of queries. That can be a useful approach. Like if we have caching at the front end, like with a CDN or a reverse HTTP proxy, that would reduce the amount of accesses to the database. We saw that Wikipedia took that approach. We can do vertical scaling by making the database machine as fast as possible and using the fastest possible disks. Okay, but then finally, once we exhaust all of those possibilities of making the database as smart as possible, adding the indexes where we can have them, where they're helpful, introducing caching at every layer, and also making the machine as fast as possible, so doing the vertical scaling. Finally, at some point, we have to think about horizontal scaling. And generally, you do that only after you've exhausted all these other ones because, as we'll see, horizontal scaling with databases introduces a lot of problems. But the first way to do horizontal scaling with databases is called read replication. And this is a pretty simple and nice idea, and it works pretty well, and it's definitely used by, for example, Wikipedia. So in this case, in this diagram, we have the main database is shown on the left-hand side here, kind of in the center. But there also are two other databases shown in the diagram. These are labeled as read replicas. So these have full copies of the data. And these are used only for reads. All the writes happen in this main or master database. So whether updates and deletes and insertions have to happen on this main database, but whenever anything is changed in this main database, this database is configured to be aware of the replicas and to send send the updates that were made to these replicas. That would be a push style, but actually very often it's done in a pull fashion, where the main database just keeps a log of all the changes that it has made recently, and the read replicas will periodically ask for the latest updates, and the main database just reads that off its log. Okay, so but by doing this, we allow the application servers. Now there are many clones of these application servers. They can now send requests to not just one database, but to 3 different databases. I mean, it just so happens that if they're doing a write, they have to go to this main or master database. But if you're doing a read, you have the choice of going to any of these 3, and you can kind of reduce the load. You can just share the load of reads across these 3, or really across these 2, most likely. And it's a very simple approach, right? There's no inconsistency that can happen here. That's one of the really nice features of this, because the writes only happen in one place. So the only challenge here is that maybe these read replicas are a little bit out of date, but there's no possibility that, if you stop writing and wait long enough, then these 3 are all going to store the exact same data. Like they'll be eventually consistent. It's called eventual consistency. And because most applications have a majority of traffic be reads as opposed to writes, this design works well, and it helps scaling. Okay. Yeah, you can't have an infinite number of read replicas, because every time, I guess, why don't you think about that for a second? What limits the number of read replicas? Why can't you have an arbitrary number of read replicas? Well, this master database or main database has to send updates to the read replicas, and if there are too many of them, then it will be overwhelmed by those transfers, right? So this main database or master database is kind of a central bottleneck. It's also a single point of failure. We'll come back to that later. And you can do a little kind of pseudo math to explore that. So if there are n replicas, then the master has to send n copies of each write. So every time there's a write on this master, that becomes not just one piece of work, but now n pieces of work. That's important. So adding replicas increases the cost of every write in the system. So eventually you get to the point where if the cost of reads and writes are the same, then and the capacity of this database to handle depending on the ratio of reads and writes, you eventually come to an equilibrium where the amount of writes sent to this main database are equal to the amount of reads sent to this cluster of databases divided by the number that they have, that there are. Or I guess the load on this main database is whatever the number of writes are times the number of read replicas. So actually in this case, the number of writes is 1, and that becomes n work. And the number of reads for every write is r. And when you equalize these, you're saying that both the main database is at its maximum capacity and the read replicas are all at their maximum capacity. And that'll only happen when the ratio of reads to writes is the same as the ratio of read replicas to the master instances. Okay, but once you go beyond that, then you will end up with more load than the master database can handle if the read replicas are at their max capacity. All right, but you can still extend. Sorry, that was a little bit convoluted, but it's a simple idea. You can go arbitrarily, though. Just because what I was saying in the last slide is that you cannot have an arbitrary number of replicas connected to one master node. but you can introduce multiple levels. Okay, and that allows you to get an even greater number of replicas. So right now in this design, the master has to send out 3 copies of every data it receives, but then that can then be in turn sent out to 3 others by these middle replicas. And in reality, you probably have more than 3. Like you might have 10 or so. But again, that depends. The optimal choice of that fan out depends on the ratio of reads to writes in your system. The more reads per write, the more fan out you can have. Okay. So in this design here, I have a few questions for you to try to answer these as we go along. There should be short answers. So where do the read requests go? Okay, actually they go to these bottom replicas, these 9 on the bottom. They do not go to this middle level. Why don't they go to this middle level? Well, just like the master, this middle level is busy pushing out replicas to these this lowest level. So we assume we're designing the system such that there's a I guess everyone is busy. Like there's a balance. There are no wasted resources. So the number of writes, in this case, maybe there are 3 times as many reads as writes. So for every 1 write, there are 3 reads that go out, or 3 propagations that go out from the master. So this master does like 4 pieces of work for every write. It has to record it itself and has to transfer them out. The same is true of these middle replicas. They receive that write and they have to propagate it out. And these ones down here receive just 1 piece of work for every write. If at the same time there are 3 times as many reads as writes, then this bottom tier would, if they're sharing all the reads, would get although I guess in this case, yeah, we actually, this is provisioned for having 9 times as many reads as writes. Yeah, actually the math there's a little funky. But anyway, the main point I wanted to make about this middle tier is that the middle tier is doing, even if it doesn't receive any reads, it still has a lot of work to do. It has just as much work to do as the master does, because every time there's a write, it receives that write and it has to propagate it. So in addition to recording it, I mean, everyone has to record the writes, but the non-leaf nodes have to also send it out. Like those writes get amplified by the fan out below. They have to duplicate those requests out to the children. All right, so where do write requests go in this case? They go to just the one master, actually. Writes only propagate downward. We can't write anywhere else. These orange nodes are all read-only replicas that are only accept changes from other databases, not directly from the application. And finally, can we add an arbitrary depth of replication levels? In other words, can we make this tree 4 levels, 5 levels, 6 levels? By doing that, we would achieve an arbitrary width. I showed in the previous slide that we couldn't, with a single layer, achieve an arbitrary width because that would introduce a really huge load on the master to replicate to all these, to 1,000 replicas. That would be way too much work for the master. But with multi-levels, can we achieve an arbitrary replication level? In fact, we can, which is cool. However, keep in mind that every time you add a layer, you're introducing additional delay. So the replicas always lag behind the master in terms of having the latest information. And that's true even more so for the 3rd layer and the 4th layer and the 5th layer. Okay, so adding multiple layers means that reads after writes could be out of date, but even more so than they were with fewer levels of replication. All right, so this design has created a kind of horizontal scaling for database reads, and actually kind of an arbitrary level of horizontal scaling, as long as we're willing to accept that slight bit of delay in propagation of writes to everyone in the system. Okay, so that's pretty cool. Notice, of course, is only for reads, because writes are still happening on the one master. That's a big deal. Okay, so if we want to use a system like this, we have an application. This application now is connected to not just one database, but to the applications are connected to the master database for writes, and so writes in SQL are things like inserts, updates, and deletes. But the app connects to a different database for reads, and the reads generally are just the select statements. Of course, it has a choice now of, in this case, 9 different read replicas to read from, and the way that would work was through some kind of load balancer. Okay, so this could be a load balancer in the same sense that I talked about a couple lectures ago with some kind of like NAT style load balancer, or it could be a software library in the application that has, in software, a list of different read replica host names, and it chooses from those. Okay. Now, I want you to stop and think about what the shortcomings of this kind of replication might be. Like, what's wrong with this scheme? What could we improve about this scheme? So the biggest things that come to my mind are, first of all, writes are not at all scalable. So every write has to go to this one database. So if there's a lot of writes in the system, if there are a lot of writes in the system, this machine is going to be overloaded, and therefore, like, the scale of your system is going to be limited in terms of writes by this one machine, this master machine. Capacity is also not scalable. This is maybe the second thing you would think of. All the data is copied on all of the replicas. So every database machine, whether it's a master or one of the read replicas, has to store the entire database. And if it's a big, huge database, like if you're trying to store YouTube videos, for example, for that entire system, there's no way you're going to be able to have enough hard drives connected to any one machine to store all those. And it's also kind of wasteful, right? You end up having a lot of duplication. Like, you don't need 9 copies of each piece of data for to keep it safe. You probably only need 3 copies at most, something like that. So we're wasting space in some sense. Like, the load balancer is picking these read replicas randomly, whereas if the load balancer was a little more clever, it could maybe know which of the read replicas had a particular piece of data and therefore direct them that way. So that's data partitioning, which we're going to go to later. That's like the more advanced version of this. Finally, coming back again to this master node, we have a single point of failure here, in addition to having a single bottleneck. If this master node goes down, we can no longer write. We still would be able to read off of all these replicas, but they would never be changing, so the system would be kind of stuck, right? Okay. All right, so let's address the single point of failure thing first. What we can do for that is a pretty simple approach where we have a secondary master, which you would typically call a standby. So I have the same basic design here on the left, but I've added a standby master, which is basically acting like a replica, except it's a special replica that's ready to take over as the master if the master dies. Okay, and that decision would probably be made by either by the standby or by the applications. It depends on the implementation. But basically, if at some point the master dies, then the system would switch over to using the standby master, and that would have its own replicas. Or these replicas could be maybe configured to switch over to the standby, but that kind of, again, depends on the implementation. So because this, it doesn't take too much to take what the system we already had, in other words, to take the system that had read replicas and turn it into one that was robust, as long as we have some way basically of switching the role of master from the first master to one of the replicas to start acting as the master later on, right? And that's basically what's happening here. The standby master is originally a replica, but it becomes the true master through some kind of failure detection. The details of which actually are kind of tricky, but let's just take that for granted. Okay. Now, we've introduced the idea of multiple masters now, but why? Let's come back to that other big shortcoming for these relational databases with replication, which is that we only had one location for writes, and so this main master was a bottleneck for writes. So why not actually have two masters where you can write to either one of them, and they replicate to each other? Like for example, if I write data here at master 1, it gets copied to master 2, or if I write data on master 2, it gets copied to master 1. Like they both listen for updates from each other, and they get propagated. Why not do that? So stop and think about that. So there are two problems. Actually, one of the problems I just thought of now and is actually pretty important, so I'll talk through that. But the problem I have listed here on the slides is inconsistency. You've introduced sort of a race condition. If you have, let's say you have two different apps, app clones writing, and they're writing variables x and y. These could be two different rows in the database, and app 1 wants to write values of 1 to both of these variables, and app 2 wants to write the value of 2 to both of those variables. But somehow our application is supposed to use a transaction, like logically x and y should be the same thing, and so we want these writes to happen kind of atomically together. So if we're using this kind of propagation, you end up with, depending on what order they come in with, you could end up with 4 possible end results where x and y take values of 1, 1, 1, 2, 2, 1, or 2, 2. And we don't want these 1, 2, and 2, 1 results because those violate the fact that there's a transaction. Of course, now that I think about it, if you're implementing transactions on each one of them, you could probably implement transactions on the synchronization as well. So actually, this is not really the reason why this doesn't happen, why this is not useful. The better reason is that this design didn't actually reduce the write load on either one of these. So every write, although we split our writes across the two masters, every one of these masters has to eventually receive all of the writes. So they might as well have just come in directly from the application. Like the fact that the second write comes in through a replication of master 2, like this path here, doesn't change the fact that master 1 is still handling all of the writes. Okay, so really the reason, and I'll make a note to fix the slide for next time and before posting it, really the reason why this it doesn't help to write to multiple masters is that the load, each one of those masters is still going to be a bottleneck. Okay. It's also true that it's harder to develop things consistently if data has more than one home, but that's a little more subtle. We'll come back to that in the next lectures on NoSQL databases. Okay. So we used read replicas to horizontally scale reads to allow a lot of read traffic, an arbitrary amount of read traffic. But we haven't been able to scale writes yet. The fundamental reason for that is because every write ends up going to every node because every node stores all the data. That also limits the capacity of the system. Okay, so I wanted to stop and think about that, but I told you the answer. We need some kind of partitioning of the data to prevent each node from storing all the data. Otherwise, we're never going to be able to scale writes or storage. Okay. The first way to do that, or the simplest way, I guess, is called functional partitioning. And this is where you have, instead of having one database to store everything, you create more than one database, and each database has a different purpose, right? So essentially what you're doing is taking the tables and splitting the tables across different databases, which means across different machines. This is often done, not necessarily for scaling, but just for like simplicity of design, for isolating different like engineering efforts. You might have an accounts database in one place. You might have an orders database in a different place, a customers database in a different place. All those could be separate. They could be behind different microservices. So part of the same principles of like isolation and parallel development apply here to databases as well as services. And because data is written only in one of those three places now, when we're updating one of these, we get more scaling of writes. We can write 3 times as much data at once, basically, because every write goes to one of 3 different machines, depending on whether it's an account write, an order write, or a customer write. The downside, though, is that because we split the tables across different databases, we no longer can join them together in queries. So the kinds of analyses we can do are quite limited. We no longer can use SQL to build queries across this whole data set. Also, there's only so much functional partitioning you can do. Like, you only have so many tables in your system. If you have 20 tables, then you can only possibly divide them into 20 different machines. And once you've done that, you now have the zero ability to do joins. So you've kind of messed up. So this is not a highly scalable design. This is a kind of scalability that might let you get 2 or 3 times as much horizontal scaling for writes and for capacity. The other approach to this, though, is called data partitioning, and this is more general because it divides data by rows instead of by tables. Okay, so functional partitioning divides data by tables. Data partitioning has the same schema and the same tables on a bunch of different nodes, but any given row, like any given data element, is assigned to one of those partitions, one of those nodes. Okay. And this is called sharding, actually, in relational databases. So a shard, think of a shard of glass. Originally, you had one big piece of glass, and you break it into different pieces. They all fit together to form the total, but there's no overlapping. Okay, they're all separate pieces. And as an example, if you think of a social media platform like Facebook, if you think of all their data, it's too big to fit in one database. So if you want to still use a relational database, which in fact Facebook does or did at least up until recent, I think they do basically for most of their data. If you want to use a relational database but scale it, you can divide the universe of Facebook into chunks, into shards. So, for example, you might have the state of Illinois, all of those users and all the activity in Illinois might somehow be on one database shard, but then a different state like Wisconsin would be on a different shard. New York State could be on a different shard, right? So somehow you divide the data. You have the same kind of data in all the different places, so that's why it's not functional partitioning. The function of the database is the same in all the shards, but the contents are different according to some rule for dividing data, which we call the sharding key. This does an assignment of rows to shards, okay? And this is something that's not supported natively by databases. There are some research databases that try to automatically do data partitioning, but generally, as far as I know, that doesn't really work super well automatically. You have to kind of, as a programmer, figure out what the best way to divide your data is, because there are a lot of ways it can go wrong, and performance can vary drastically depending on what rule you use, and you really want it to be balanced, and you want to, have the activity be as separate and separate as possible without having to cross those boundaries. Okay, so there's a lot of kind of like tuning and hacking at the application level to get this to work, as we'll see. But to illustrate this, let's look at a little example. So this is like a mini social media application where we have users and we have posts by those users. And I have 2 shards, so these are 2 different machines running databases that are storing the same kind of data but different subsets of the data. And I'm using the rule that the shard ID is the user ID of the row mod 2. So basically all of the even numbered user data is on shard 0 and all the odd numbered user data is in shard 2. And every table has a user column. That's how I was able to use this very simple rule to do the sharding. So you can see that the users are split, right? 3 users on this side and 2 on the other side. It's roughly balanced because the rule I used is not biased toward one shard or the other if the user numbers are generated sequentially or randomly. So if we want to, for example, query for all the posts by Steve, so this, if you know SQL, that would be select star from post, natural join user, where user equals 1. Natural join, if you haven't seen that, does a join using the columns with the same names are set to be equal. So it would take these users, look for the posts that have that match up the users, and then finally it filters out for just the user equals 0, which is Steve. So it would be basically querying for these posts here. To implement this query, how do you handle the shards in this case? I'm asking you, think about it. Well, if we know that this query actually is specifically filtering by user, and the sharding is done by user. So for that reason, we can do the query entirely on shard 0. Okay, but we need a little bit of programmer awareness and application level hacking to make that decision. Okay, fundamentally, unless we really know the meaning of the relationship between this shard key and the query, it would be hard to make that judgment automatically. Although you might be able to, actually. I guess you could programmatically figure it out, but yeah, so I'm not saying, yeah. But it just so happens that in this case, this is a query that actually is very well designed for this type of sharding. So this sharding supports these kinds of queries very well, because any query like this for any different user will always be associated with one shard or the other, and it won't have to ask for both shards. That's important. In this case, I have a slightly more expanded version of this example, where not only do I have users and posts, I also have friend relationships. So for every user, I can have a set of rows that connect my user to a bunch of friends. Okay? And, whoops. I want to implement the query now to get the latest 10 posts from Steve's friends. So, I mean, if you know SQL, this is the query that would do it, or a version of the query that would do it. I have to join the, well, in this case, I'm joining all 3 tables because I'm using the name Steve instead of the ID 0. I guess I assumed I didn't know that it was ID 0 ahead of time. But anyway, that just makes it a little more complex. Yeah. So I end up matching this user table to the friends table, and that gives me, in this case, 4 rows, and then I match the friend IDs with the user IDs and posts. So basically, I take all the friend IDs and match those to posts to find all the corresponding posts. And I'm limiting by 10, ordering by date. So I only want to get the top 10 by date. So how would you implement that across the sharded database? Stop and think about that. Now, the reason I brought up this example to contrast with the last one is it's much more complex. In this first shard, I have all the information about Steve. Like, all of my posts are in this one shard, and all of my friends are listed in this shard. However, my friends' posts could be in any of the shards, because my friends can have any ID. I'm not limited to having friends just with even numbered IDs, or in general to have the same shard number as me. So I can do part of the query in this one shard, like if I can figure out my user ID in this first shard, and I can get my list of friends in this first shard, but then I have to scan through the posts table in all 3 of the shards, or all of the shards. I showed 3 in this example, but I'm just trying to show that there could be any number of shards. So this query I have here, actually, and even this query as it's written, won't work in the other table, in the other shards, because if you try to the one user row I need to do this join to get the user ID is only present in the first shard. So I have to do like first I have to do a query to get the user ID of 0, and then build a second query that does a similar thing where it gets posts, or sorry, I have to get all my friends from the first shard, and then I have to use that list of friends to build a second query and send that query to the other shards, and that'll actually be a very long query because it'll be explicitly listing out different friends. And I'll have to get the top 10 posts in terms of date from all of the shards, and then manually merge them together, sort them, and get the latest 10. So all of that basically has to be done manually in your application level code to get the sharding to work. So usually you have some work in your application to translate from API calls or functionality to SQL queries, or like maybe you're using something like Hibernate or some library to do it for you. But anyway, in this case, you have to now not just translate to SQL, but think about the logic that has to like a much more complex translation of taking the function you want to implement and breaking it into multiple steps and figuring out what has to run in what shard to get that to work. Okay. So that was just a very brief introduction to sharding. Actually, I think the book does a great job on this whole lecture's topic, both with the sharding and the read replicas. So please make sure you read that if you haven't already done so. Regarding sharding, though, to summarize, we have pros and cons. So on the pro side, by sharding, we're able to scale the capacity. Like we can store more data because the data is stored in only one place. The data is consistent. There weren't any issues with like storing data, trying to write it in two different places and having a race condition. So it's really easy to get consistency of data. If we choose a good sharding key, we also end up with balanced data. So, for example, the first example I gave of like different states of the United States was not the best choice because some states have very few users. However, using some kind of numeric hash or something does get a balanced result. There's a trade-off there, though, because then you might lose. It would be nice to have all the users that kind of know each other that are nearby in one shard, because then they would tend to be seeing each other's data more often. But if you use some kind of arbitrary hash, then you lose that locality. We saw that with sharding, a lot of the queries we ran only involved one shard or only a few shards. That's really nice. There's no central bottleneck for those. We can scale the capacity, the ability to handle more writes by just adding more nodes. Because when we do that, each request only has a fixed amount of work. The amount of work per request doesn't scale as we scale the system. On the downside, there was basically the biggest downsides were the complexity. We can't use plain SQL and expect it to work. The references between tables are kind of broken because the rows are going to be split across different shards. So we have a lot of manually stitching together those joins that would originally happen very naturally in SQL. It's also possible that if we chose a sharding key badly, then the load would be imbalanced. And when we're talking about load here, we mean both the capacity, like the amount of data stored, but also the traffic. And finally, some of the queries, in addition to being kind of hard to build, sometimes they involve all the shards. Like that one that looked for the recent posts by my friends, because my friends in this case were distributed across all the shards. That's a real downside. It basically eliminates, if we have a lot of those kinds of queries, it means maybe we did a poor job sharding. We should try to choose a different sharding strategy so that we eliminate those queries that involve all the shards. But if we can't avoid that, in general, we can't avoid that for every type of query because of all the different possible ways of mixing and matching the data together. But by doing that, we're limiting the capacity for handling queries by a single machine speed, right? If a single machine can only handle 100 requests per second, then no matter how many machines we add, if every machine is involved in one of these requests, we can only handle 100 of those requests per second, right? That's fundamentally the problem with involving all of the shards in a request. And you can do some simple math or try to demonstrate this with math for the scaling. So here I'm saying there's n nodes and there are r requests in total that you want to make per second. This is the rate of requests, r. And then finally we have a constant c to indicate the maximum rate of requests per node. So this is like the capacity in terms of the throughput, I guess. Not storage capacity, but the request per second capacity. And I have three different scenarios for how requests are handled. If a request is sent to just one node, this is the ideal case, and it can be handled by one node. This is if your sharding aligns well with your queries. then the maximum request rate is going to be the number of nodes times the capacity of every node. Because as you add more nodes, they each can handle capacity independently. They don't, adding a node doesn't introduce more load to the other nodes if that node starts accepting requests. So that's a scalable design. So the formula here for the maximum request rate is n times c. So there's a factor of n in there. So as we add more nodes, the total request rate goes up. If we send each request to a constant number of nodes, k, it's the same basic idea. We still get a linear scaling with adding more nodes. It's just that there's a different slope to that scaling. So it's still big O of nc. So it's still scalable in a linear way, which is nice. So whether we have one node handling a request or a constant number of nodes handling a request, those are both really good ways of scaling. On the other hand, though, if a request is sent to, if all these requests are sent to every node each time, we get the opposite, which is a totally unscalable system. So in that case, the total capacity of the system is going to be equal to the capacity of a single machine. And there's no factor of n in there. It does not go up when you add more machines. If you add more machines, that doesn't change the fact that each one of those previous machines has to be capable of handling all the requests that go through the system, right? That's a big problem. All right, so to summarize today's lecture on relational database scalability, I showed basically two big approaches to making these relational databases scalable. So the first one was read replicas. These are both horizontal scaling approaches. With read replicas, we added a bunch of read-only copies of the data. Writes happened in a master node, and those were propagated down to the read replicas. And this was a useful approach because first of all, it's really simple, right? But also, typically, database traffic has a lot of reads, more so than writes. So there's a benefit to doing this, right? You can handle those reads with replicas and just have your single bottleneck. You're still going to have a bottleneck in writes on that master, but you can have a lot more reads happening through the replicas. But if we want to scale either the capacity or the writes, we have to do data partitioning and basically not store every data in every node. So somehow we have to assign each data row or element to a single home node, which we call a shard in the case of relational databases. So with sharding, we come up with some scheme for dividing the data across different nodes, and they're separate databases. They don't really know about each other at a database level, but at an application level, you have to build some logic to stitch together those databases and make them work together. So it introduces a lot of complexity. We lose the power of SQL to aggregate things automatically and to do query planning and optimization and stuff like that across the whole system. We have to build out the application level. But it's a tool that we can use, and it lets SQL writes scale. This is being used by basically any big system you know of. Facebook is really famous for sharding the heck out of their system and getting a ton of scalability out of MySQL databases. Next time, we're going to move on to NoSQL databases, which also do data partitioning, but they take an even more extreme approach than the SQL sharding to get even more horizontal scaling. Okay, so it takes the same basic idea of data partitioning and sharding and takes that to an extreme by limiting the number of tables and all kinds of other stuff. All right, so I hope you enjoyed that and learned from it, and see you next time.